Okay, now this nonlinear relationship that we found between the drain current or the drain source current and the VDS. So we're talking really about IDS versus VDS, right? We realized it's not really a linear relationship. So what we thought that about like the transistor being really a distributed resistor, at least generally, it's not really correct. It wasn't the correct assumption. It was kind of like a resistor, but well, if it was a resistor, VDS and IDS should have had a linear relationship, and that well, the constant that was really basically relating them to each other was the resistance, right? However, I do appreciate the fact that if VDS is actually quite small, let's say if VDS is much smaller than 2 times VGS minus VTH, then I can say that, let's give you some numerical examples. Let's say my VDS is, I don't know, 0.05, or well, something easier. So 0.1, and let's say my VGS minus VTH is, I don't know, 0.5, right? Or even like larger than that. Let's say it's even 1 volt. 2 times VGS minus VTH is 1 volt, right? These are just random numbers. This doesn't mean that it's always like that or like even in that order of magnitude, but just to give you an idea. Now, what would be the VDS squared? It would be, well, 0.01, right? Now you can see that, well, this is going to be 0.1, this is 0.01, so it's much smaller than the other guy, like this term is going to be much smaller than this term, so I can approximate the ID to be almost equal to mu and C ox W over L, and then I can say that it's VGS minus VTH times VDS. So the VDS squared goes away. By the way, this, if you're wondering where did this 1 over 2 goes, well, once this goes away, this 2 and 1 over 2 cancel out each other, right? So what I'm trying to say is that inside the bracket, you can see that I can kind of say that I can ignore this as long as the VDS is a small voltage. So if this is my NMOS transistor, this is the gate and this is the drain and the source. If this, let's say, source is 0, if I connected drain to some voltage source VD, if VD is in the order of like, I don't know, very small values like 0.1 or 0.2 or something like that, or even less than that, let's say 0.01 or 0. Like 10 millivolts, 20 millivolts, 30 millivolts, something like that, you can imagine that, well, this expression that we found kind of reduces to some sort of a linear expression. Now that we have a linear relationship between IDS and VDS, why is it linear? Because, well, VGS minus VTH is actually constant. And, well, these are a bunch of constant parameters, mu n, C ox, W, and L, right? By the way, another thing to note is that all of these things kind of like make sense to be like basically this. We didn't talk about this equation and like if all these parameters being here makes sense, but if you think about it, ID having a linear relationship with mu n is something that does make sense because, well, the current really it could like basically it is expected to be proportional to the mobility of electrons. It is expected to be proportional to how big is the capacitor, the oxide capacitor, because we said that the bigger the oxide the capacitor, the more free electrons I'm going to have for the same voltage at the gate. So like more free electrons means for more current, more charge means more current. It is expected to be basically proportional to W and inversely proportional to L because, well, the longer the channel, the less current I'm going to have, and the wider the channel, the more current I'm going to have. So all of these stuff does make sense. Now, all of like basically what I was saying is that this entire thing is really constant as long as I don't change the gate voltage. Constant as long as Vg is constant. So I can say that, well, that's 1 over R because of Ohm's law. So I can say that the R on, the resistance of my channel is going to be 1 over this constant. So 1 over mu n C ox W over L VGS minus VTH, right? By the way, another thing to note is that I'm using mu n, which is the mobility of electrons. And the reason for that is that the kind of a MOSFET transistor that we are talking about is the N-type MOSFET. The reason is that the the charge carriers that are actually causing current for me in the channel are electrons, simply because the voltage at the gate is actually positive. We're going to be talking about another type of, similar to NPN and PNP, we're going to be talking about another type of MOSFET, which is a P-type MOSFET. So this is a really N-type MOSFET, or NMOS, and then we're going to be talking about a PMOS by the end of this lecture, hopefully. Okay. So now we have a resistance that is controlled by the gate source voltage. You can see that it's dependent on VGS. So what we thought it's going to be true, it is indeed true. But then we know that this resistance, like we do have a purely resistive kind of a behavior when the voltage at the drain source voltage, the voltage difference between drain source is actually very small. Okay. So, and then you can see that if I make the VGS equal to VTH, well, this on resistance becomes infinity, meaning that, well, at this point my transistor is not on yet, so I don't have any channel yet. So you can actually imagine that I'm not going to have any kind of, basically the resistance between drain and source is going to be infinity. This is the reason that MOSFETs are actually really good for digital. Like this is the mode of operation that we actually use MOSFET, or the region of operation that we use MOSFETs in digital electronics. So the entire digital electronic field, the field of digital electronics, and whatever you have heard about digital circuits and digital electronics, are based on simple switches that should be turned on or off. So like basically, you have seen switches in electrical circuits before, that we show them with this symbol. We say that if this is basically X and this is Y, we could have the switch on and off, right? The switch could be simply created by a MOSFET that, well, I have source here, I have drain here, and I have a gate here. And if V gate is less than V threshold, this MOSFET is off, so that there is an open circuit between drain and source. And if V gate is greater than V threshold, and generally we try to actually make this a lot greater than V threshold, so that nothing, like basically regardless of what is the drain voltage or what is the source voltage, I don't have any pinch off. I don't even get close to that. I always can assume that the VGS is actually so large that I can always assume that VDS is much smaller than VGS minus VTH. Therefore, I can actually assume that I have a really good connection between drain and source, because as long as my VGS is actually really large, you can see that this resistance becomes smaller and smaller and smaller. And you can see that, well, if the VGS is large enough, I could be able to approximate R on being almost zero. So I could approximate the switch causing a short circuit between drain and source. Okay, so this is not really the focus of this course. This is just basically telling you that MOSFETs are the main way, or like the basically 99.9% of switches in the world on any kind of electronic system or circuit are basically made using MOSFETs. At least like electronic circuits. When you're talking about power systems, things are different at high voltages, but in electronic systems, in any electronic gadget, any integrated circuit, the switches are made using MOSFETs. And the MOSFETs, when they're working as a switch, they're either in the off region when VG is smaller than VTH, or they're basically in this region where VGS is much greater than the V threshold, and also basically which results in VGS being or VGS minus VTH being a lot greater than VDS. Okay, so in this situation we have a short circuit between drain and source because the resistance is going to be very small, and in this situation we have an open circuit between the drain and source.